Thomas Stadelmann, is an AI engineer at deepset. He loves to bring innovation to deepset's commercial LLM platform while also contributing its open source LLM framework, Haystack. His passion for today's LLM-based solutions in information retrieval was engendered during a decade of working on a professional search applications. Let's go and know more about how to go from zero to production with LLMs.
Hi, Fabiana. Thanks a lot. Yeah, I'm happy to take you on a journey that we had together with one of our customers, a journey of an LLM app. And yeah, I hope I can give you a glimpse of what it means to bring such a system from zero to production. So let's get started. So just quick words about me. You already mentioned it. So I have my background in search applications. I've been working in the field over 13 years, mainly on commercial search applications. And yeah, since I joined deepset, I still work on search applications, but more focused on LLM-based search systems, of course. And at deepset, we do this by providing our open source framework Haystack and also our commercial product deepset Cloud. So I'm AI engineer and software engineer at deepset, and if you like, you can find me on Twitter, LinkedIn, and GitHub. But let's get started. We have quite some agenda here. So first, I want to introduce you to this nice LLM app, and then afterwards jump into how they did it. How did they do prototyping and evaluation, deployment, monitoring, and observability? What does that mean when running a LLM app in production? And then the last part is a bit more technical. We want to look behind the scenes because, yeah, you know, if you have such a system, it seems like, okay, I have it in production and that's it. Well, we'll answer that question. So first, I want to introduce you the LLM app that we are talking about. So sorry for that, it's German, but in a bit, we'll have the chance to try it out live, and then we can also translate it into English. So what is it? It's a system that is able to answer questions about recent news articles from a major German online publisher. It's called Zeit, and you can compare it to publishers on the English side, like the New York Times or Washington Post, but for the German market, obviously. And the answer contain citations, so you can check, verify where does the answer come from which articles, then you can jump into the articles and read them. So one of the main challenges of this system was actually dealing with recentness, because, you know, news are very, very biased to recentness. Things can change very, very quickly, and this was one of the major challenges, and we'll see in a bit why this is quite difficult in systems. We've already learned about RAG systems, and we'll also see how they did it. Also, prompt injection we already heard in the previous talk. This was also one of the problems they had to deal with, because obviously they do not want their raw text being exposed to the users, but rather just have the articles then in a nice way delivered to their users. And of course, one of the things is sometimes, the articles also are based on opinions, and they wanted to have it like obvious to the reader that an answer is based on an opinion. And this is also quite challenging for such systems, because most of the time they take like, okay, this is a fact, and they treat information always the same. Like, okay, is it now an opinion or is it a fact? And of course, what's very, very crucial for such a publisher, I mean, trust is everything. We've also heard about hallucinations. If the system misbehaves and just gives you wrong information, yeah, it can be very, very bad for such a big name. But I would say let's just jump in and give it a try. So I'm gonna share my screen. Now we're doing the trick and just using Google Translate to convert it to English. And you can see the user interface, yeah, like a basic search interface. And we can now ask a question. So this is translated. I have to say I have to ask it in German because the prompt is in German that it works. So what we are asking is what is healthy for the heart, so for the human heart. And then, as you can see, you get a response within seconds, and you also have these nice citations that you can verify. Is this information really coming from there? What is more about this? And you can also say, okay, this is good or this is a bad answer. Okay, yeah, that's basically it. Also, you can find related sources of it. That's basically the documents that have been used for RAG. So that's pretty interesting. Okay, let's jump back into our presentation. Now, knowing the system, how did they do it? First, I'm coming back to this. I know we've already seen what RAG is, but I think it's crucial to just get a glimpse of it. So I'm quickly repeat this because why are we doing RAG? LLMs basically do not know the answer to everything. They have been trained at a certain point in time, and everything that comes after it, they basically don't know unless you update them. And updating is slow, expensive, and inefficient. And of course, for such companies that have their own data and do not rely on web data, it doesn't really make sense to provide their data to different parties. Also, LLMs are bad at incorporating reasonness of learned facts. So if you ask something, just about a fact, most of the time, the information the models have been trained on doesn't contain any data. So the model literally doesn't know, okay, from when is this information? Is it still valid or is it not valid? And that's also a problem. And as we've already seen in the previous talk, they are prone to run wild without precise instructions. But they are good at following some instructions. And that's where RAG comes into play. We can help them by giving the relevant context. And yeah, then they can follow the instructions accurately. So how do we do that? Just like a brief schema again. So this is basically how RAG works. We have a question. Then we have some kind of, we call this retriever in most frameworks. Also in Haystack, it's called retriever. And the retriever does nothing else like a search application. So it just searches the data store. This can be some kind of vector store or traditional search application, and provides the documents. And the documents we can use and enrich the prompt. So the prompt is just a text. I bet everybody of you has already seen a prompt. And we can create prompt templates. So we can say, okay, there's an instruction, answer the question based on this context. And we have placeholders, so we can add the documents and we can add the query. And then we have this rendered prompt, for example, like this. Answer the question based on this context. For the question, did SBB collect? If we provide the relevant passage from the Wikipedia article, it will give us a nice answer and answer with yes. So it's fed into the LLM and then the answer comes out. So this is basically all about RAG. Now, how do we choose, or how did they choose the right components, or which components are crucial for RAG? So we've already seen we have a retriever, we have an LLM, so a model, and obviously also the prompt or the prompt template are important. And I think that's very, very important to understand that all of these three components can have a significant impact on the results. So if we talk about it, also how to choose the right, say, retrieving method or the right LLM model or the right prompt, we are dealing with a lot of options. A lot of options times a lot of options times a lot of options is like, yeah, it's really amazing how many good models are out there. So now we are dealing with, okay, how can we even choose? This is really a problem now. Let's start with the retriever. So just to give you an idea about what kind of things you can do. So you can do like classical keyword search called BN25 here. You can do vector search. You can choose between different models here, and you can combine them. You can do hybrid search, so combining keyword search and vector search. And then on top, you can actually also put something called re-rankers. So you can, after the retrieval step, re-rank them, for example, biased by recency. That's, for example, what Scite did. And now let's go to the model. I think, yeah, maybe 1 year ago, it was a lot easier because there was basically just one very good model with GPT-3.5 Turbo. Now we are dealing with like a really, really zoo of models with GPT-4, Claude 3, Llama 3 just popped in 1 or 2 weeks ago, Mixtral, whatever. So it's really, yeah, it's not just a choice between 2 or 3, but there's a lot. And also here, when you want to make a decision, it's not just about quality. It's also, for example, about policies. Like, okay, can I send my data to such an API provider? Do I want to host it myself? Can I host it myself? Yeah, whatever. On the prompt side, you also just can imagine that you have a lot of options. You can, for example, put a setting like you are a scientific researcher or you are a publishing researcher. You can also bring or make the model provide citations, as we saw in the example. You can say, okay, it should cite the information that it got from the right documents. And you can also bias it towards this direction. Hey, please, if you do not get the relevant information, please answer with, I don't know. So yeah, I think it's crucial to understand each of these things can have significant impact. And that's also what we saw in this project, because yeah, they basically spent a lot of time on all of these. So how do you do that? Or how did they do that? So they used one of our tools to being able, like, switching components very, very quickly. So you can see here on the right side a graphical user interface, and on the left side a YAML. And the YAML is basically just a definition of the pipeline, and you can switch any values very, very quickly. So for example, the retrieval model, or you can change the LLM model or the prompt that you can see here. And yeah, as I said, that's pretty crucial. Let's jump a bit more into the details of these 3 components. So retriever, what's important when it comes to prototyping and evaluating with it? The good thing about retriever is you can rely on a very, very good established way of evaluating it that dates back to, I think it started in the 1970s or something, how to do information retrieval evaluation. But the key parts for when you get started is you really want to automate this. You want to analyze results quickly, and what will be mostly affecting your costs is creating an evaluation data set. We'll see this in a bit, what that means. If you have all this, then you can calculate metrics like, for example, recall, that can answer your question like how many of the relevant documents did the retriever return. And on this, you can basically, yeah, assert that it's good or not so good. So how do you create such a evaluation data set? So basically what you want is you want pairs between queries and the relevant documents. And one thing they, for example, did is you can use like an interleaving strategy. You can use different approaches of retrievers and just merge the results. And then you have some employees or users even that provide feedback and just mark them as relevant or not. And this way you can collect a lot of data points in a very, very short time. And then when you have that kind of data, like for example here also the second one who lives in a lake next to Hogwarts, you can also have two relevant documents, of course. You feed through the retriever, you get results. The results you compare with these gold standard documents, and then you can calculate metrics. So this is a very, very systematic and yeah, quite easy to understand way of evaluating things. So now we are going to model and prompt how to evaluate that. And we already heard in the very, very first talk today, this can be like very difficult because it's like an open-ended evaluation. These RAG models can generate basically anything, and it's very, very hard to evaluate it thoroughly and systematically, especially without tools. It can be very time-consuming and expensive. So what you really want is at least you want tools that can support you. And I think anybody of you might have already seen such an interface where you, I think it's, yeah, first one was a chat arena or I think how it's called. So you basically just have multiple pipelines or multiple models that you can compare. And in this interface, you can also change the prompt template, yeah, just quickly. And then you get immediately, you can issue queries, you get immediately results, you can leave feedback, and afterwards then compare, okay, what was the best one? What combination of model and prompt gave the best answers? So that's, I would say, a semi-systematic way of doing this. Of course, there's a lot of humans in the loop. Another way is basically using automated metrics. And I want to introduce you to two of them, groundedness and answer ratio. We see them in a bit. When you have this, then you can basically just start experiments with these with your pipelines that you configured, and just calculate these scores based on queries that you provided. You can sort them. You can have your own, basically your own use case specific leaderboard for the combinations and so on. I think about latency we don't need to talk much about. It's obvious that some models are faster, some are not so fast. So it's really use case dependent if you want to use like a slower model like GPT-4 or want to go with a faster model. But let's dive into groundedness. So I want to give you an example. So you get an answer from an LLM, like for example, 2 sentences. DeepSet was founded in 2018. Products of DeepSet are Haystack Farm and OpenSearch. Spoiler, the last one is a hallucination. It's not right. OpenSearch is not from DeepSet. So what can you do? Basically, if you had a model that can compare an answer sentence with the documents that you have fed into the model during RAG, and this emitted a value, like for example, yeah, 97%, 29% of groundedness, which means basically, okay, this is the degree to which the answer is supported by the document. You can also think about it as the opposite of hallucinations. If you have a very, very low score, then yeah, it's a very high chance that it's a hallucination. And if you had that, and if you calculated that for each of the RAG documents, then you can basically say, okay, I take the max of them. I have 97%, so probably this is very, very grounded. On the other hand, if you look at the second sentence, this seems to be not grounded in the first one at all. In the second, okay, there's something. Actually, this document talks about products of DeepSet, which are Haystack and Farm, but probably it didn't name OpenSearch, so it ended up with 62%. and then another irrelevant document. And then we end up with 62, and we have a score that is that can show us, okay, hey, maybe there's an hallucination. So just to give you a bit insights, what kind of models we are talking about here, one of some that we are not using, but that is very nice to explain how that works is BERT score, because you can make these nice visualizations. So just think about, on the left side, you have all the tokens, so the words of the answer, and on the bottom, you have all the words of the source, so of the reg document. And now what BERT score basically does, it measures semantic similarity between those tokens. So you can see whenever you have a dark diagonal, then that basically means that parts of the answers are basically taken as is, or are very close to parts of the source. On the other hand, if you have very light parts, then that means, okay, there's no semantic overlap, so also no groundedness. And yeah, you can basically use such models or better models. So for example, you can also use cross encoders that work very well with calculating such numbers. Or you can even use LLMs. So how do you build now metrics from this? If I have such a score, such a groundedness score for each sentence, I can easily aggregate them for the whole answer. I can just, for example, average them or max them or min them. It's up to your use case. And this way I can build a groundedness score, which is basically, as I said, degree to which an answer is supported by the retrieved documents. So now, what about these kind of answers? The most popular Wikipedia article is not mentioned in the provided documents. The answer can't be found in the text. So the model basically tells us it cannot find the answer in the documents. So obviously the groundedness score would be very, very low. It basically doesn't make sense. So what we need for this is actually something else. And that's very important. It's a very closely related metric to the groundedness score. We call it no answer ratio. You can also take the inverse, which is answer ratio. No answer ratio gives you the percentage of queries the LLM refused to answer. And now if you think about what you want to optimize basically your system for, you want to get a very, very high groundedness value, but you want to also ensure that the no answer ratio is not too high. Because if your model doesn't answer any questions, of course, it's quite useless, right? So these two basically always come together. So yeah, that's also something that the customer here used to build the system. Let's wrap it up. So what were the key factors to success for this system? Quickly iterating on retriever, model, and prompt. So they tried over 200 combinations. And that's only the combination that we could track, because we couldn't track basically which kind of different prompts they used. So I would expect it was way over 300. And that's a lot, of course. So they found a way to handle recency. They use hybrid retrieval using a recency biased re-ranker. And they found a way to handle prompt injections by inserting a custom query classifier model. It just basically built, or trained a model to fit their needs and just inserted it into the Haystack pipeline. And they found a way to handle opinions by doing clever prompt engineering. So now that we know how to build such a system, let's quickly look into how to deploy and monitor such a system, because you want to maintain such a system also, you want to run it. So what are parts of the system? We have four main parts, actually. We have an indexing pipeline, which basically gets files or the data, converts it into text, pre-processes it, and then we store it into, we call it document store, you can call it vector store, or you can use traditional search engines. Yeah, we've already seen there's Milvis, there's There are other ones, VRV8, OpenSearch, Elasticsearch, Pinecone, you name it, Quadrant. And the third part is the query pipeline. So we've seen retriever and prompt node. Prompt node is basically the thing that renders the prompt and feeds it into a model such as Hugging Face, OpenAI, models on AWS, Bedrock, Azure, whatever. And is that all there is? What else is needed to run such a LLM app? Not quite. We need a bit more. Once it's up, you definitely need to make sure that it's behaving correctly, right? You do not want to have errors. So you need to store the logs of indexing and query pipeline somewhere. You want to show them to whoever develops such a system into a monitoring tool. And what's also quite crucial is the query log. So if you want to collect feedback, you definitely need to store the queries and the results somewhere. And that's also crucial for providing observability features. I'll talk about this in a minute. So just to give you an idea, what does monitoring or how could monitoring look like? You want to keep track of queries, user feedback, and errors. So you want to, for example, show the latest queries. You want to collect the feedback, show aggregate metrics like correct answers, also the latency, accuracy of the pipeline, you name it. And of course, the logs. What do we mean with observability? As we saw, there's something like the groundedness score. And now think about it. You deploy such a system. You're using an LLM that sits behind an API. And now it could be also that the API provider just changes the model underneath the API. You do not know. So you definitely want to make sure that the model doesn't go off. And especially in this case of this LLM app, it was super crucial that it doesn't hallucinate. So you can build something that calculates your groundedness score just live on top of all the queries, and you can monitor that. And to build such a system, I want to quickly wrap it up by giving you a glimpse by looking behind the scenes. So what does it mean to provide such a query log at scale? Because that's the data this observability service is built upon. Once we started as a startup, basically as a startup, you build anything as a monolith, and you just feed your data into one database, and then it gets bigger and bigger and bigger. And at some point, you have so much pain with it that you really need to build it like you should have built it from scratch to make it possible to scale well. And that's what we did. So how does it work to get such query logs? So we have our query pipeline that emits just logs into a file. And then there's some other process that is completely separated from it that reads the logs and emits events out of it. You can think about any event system. This could be Kafka. This could be SQS on AWS, whatever. And here you can subscribe it for any use case you want. So, for example, one of them is the observability service. It just consumes this data, has its own database, and calculates the groundedness score and provides it to the users. Also, feedback we use from these events. And also, when we look at this monitoring interface that we saw, it actually uses two data stores, one in-memory database, which is basically a hot storage, which just stores the latest events, but it's very, very quick. And then there's an analytics service that stores all of the queries basically, and on which you can run analytics and get more insights that require more data. Yeah, that's basically it about looking behind the scenes. To give you a quick conclusion, I think what we've learned here is that it's very, very crucial to quickly iterate on the different possibilities for retriever, model, and prompt. All of them are very, very crucial for getting a good solution. Also, finding the right components and parameters is highly use case specific. So for example, here we were dealing with something that needed to be recency biased. Not any search application or any LLM will have this requirements. Also, being so crucial about not having hallucinations. Maybe you definitely don't want them, but there might be use cases where it's not that super important, like for example, code search or something. Bottom line, the story of an LLM app doesn't end with a working app. I hope I could show you that. There's a lot more going on behind the scenes, as we've seen. And going from zero to production is challenging, but it's possible when using the right tooling. And it's important that the guys that have the use case and want to really solve a solution, that they can focus on their use case and on the solution and not have to deal with the technical details. Yeah, that's basically it from my side. Thanks a lot for having me.